So let me talk a bit on few contact forces, majorly normal reaction and tension force. So tension force first. Now what is tension force? When a certain body is being pulled by a string will be able to pull something, not push anything. So we will be generally talking about the tension force in the string. So one of a simple example would be a body suspended by a string. So what is happening? Why is this body not falling down? Why is this body not going down? Because that body, now why should that body go down, by the way? The body should go down, or there are chances of the body going down because the earth is pulling it. By how much force? By a certain force which we calculate using the formula F is equal to gmm by r square, and we ultimately get it as mg. By that much of force, the earth is pulling this body. So why is the body not going down? Because the net force on the body must be zero. That is one of the laws of Newton. So why is the net force zero? Because the string which is attached on top is also pulling it. You can imagine it as a spring which gets stretched a bit and pulls. So this string is also pulling it up. So that pull from the string is called tension force. How much will be the value of the tension force? We are going to study. Right now I am just telling you that where is the tension force generated and how it acts. So I've talked about this end. I'm going to talk about the rest of the string also, all up till the top end. So I'll just demonstrate how it works. If Mr. Laksh can please come. So he's holding a string in his hand, and I'm asking him to just hold it, don't pull it. Just hold the string and don't pull it. Now what I'm going to do is I'm going to pull the string. I'm going to pull the string. Right now it is slack, it is loose, and now I'm asking him to hold. He is very much capable of holding the string. I am pulling the string. Now I've pulled a certain amount. I wish I had a spring balance to show you how much I pulled by. So it is a good amount I'm pulling by, at least 5-6 kg force I'm pulling by, and he's holding it. So I feel as if he is pulling me and I'm holding. Are you pulling me? So to hold, he has to pull. So to hold the string, he is pulling me. So if I ask him after 5 minutes, or we look at a situation after some time, then who was pulling whom will be forgotten. It is immaterial that which end generated the force. The force ultimately is he is pulling me that side and I am pulling him this side using the string. So this string is having action of pull on his hand and a pull on my hand. So, thank you. One more thing before he goes away, I'll just demonstrate a better way of pulling him since I could not manage. Just put your hand like this. Now suppose I have put this end onto a wall. So suppose this hand is a wall, and I pull this end with the equal amount. This time I am managing double the force what I managed last time. He would tell that. Is it? So I am pulling it by a much larger force. What I have used is, I have used a wall. So this is the wall. I am just spending my energy on one part of the string. So if you ask me, actually in this case when there is no wall, I am spending my energy on both part of the string actually. So I am going to discuss this case also later. Thank you. So discussing that case, or in fact going on to this mass was pulling the string. Why was the mass pulling the string? Because the mass was getting pulled by earth. So the mass was pulling the string. Since it pulled the string had an equal and opposite reaction. So that's Newton's third law. So it had an equal and opposite reaction. It pulled it up by some force. We'll inspect how much is that force. Maybe it is equal to mg, greater than mg, less than mg. We'll see that. And that will also be governed by some law. Now, what has happened to the other end of the string? The other end is pulling the wall down. So I'll just repeat the sequence. This mass was being pulled by earth. So the mass pulled the string down where it was attached. String put an equal and opposite reaction and pulled it up. String got stretched, or it came under tension, and it pulls the other end down. So a stretched string pulls both the ends. It pulls both the ends. You don't have to have a person over here to pull. It is the string itself gets stretched and both the ends are pulled. If it is a massless string, then the pull on both the ends will be of the same value. If the string is having some mass and the things are moving and all, we'll see what will be the tension on one end and the other end. Will they be same or not? We are going to cover that later on. But the point what I'm trying to make over here is, one, any stretched string will pull both its ends. In this very case, had I been on a roller skates and pulled him, I would have gone forward. I would have gone forward because the string pulls me, not like that person pulls me. So I don't need a person for that. Just imagine if that was a string and I pull the string. If it is hooked onto some point and if I pull the string, what happens is I get pulled forward. I am getting pulled forward. That is one way of pulling yourself. You pull the string and the string will pull you. Like if you have to moor a boat or something, you throw the rope on the other boat and you pull the boat, both ends will get pulled wherever the moor has been thrown. So a stretched string under tension will pull both the ends, and the pull on both the ends will be same if it is a massless string. For sure, if it is a massless string, the pull on both the ends will be the same. If the string is having a mass, then in what case it will be same, we'll discuss later. Now, if I inspect any one portion of the string in between, any one given point, so I'll put a different mark on it. So this point, what is happening to that? That point is getting ripped off. The forces are trying to rip it off. It is the electromagnetic forces, what we were talking earlier, is keeping the things together, but it is the tension force is trying to rip it off. What is the value of this tension force? All same. So at any given point, you have this ripping force, what is going away on both sides at any given point. So if we draw all the pairs, ultimately towards the end, the last point, the end point, it is a singleton for this will be pulled in and the other end will be pulled in. The counterpart will be on the body which it is attached to. Say this is the wall. The wall is getting pulled in. So wall is trying to pull the rope that side. Here the man, some man maybe or an object is trying to pull the rope this side. So these are the tension forces in a rope, and we are going to draw only the two at the two ends, pulling the two ends. Mind you, we will not draw just one. We will draw the pair. We will draw both at both the ends. The pairs are, by the way, this way. Pulling any one section from this dot to that dot, pulling both the ends. Pulling both the ends. So those are the pairs. Okay, so that's your tension force. And then I also came with a setup of pulling Mr. Lakshya with a greater strength. And what was that? I said that one end is attached to the wall. So my one hand served as the wall, by the way, and it went through around his hand, and I was pulling this end. I was pulling this end with a certain force F. So what happened? The string pulled me back with the equal and opposite force, which I called as the tension of the string. So your T was equal to F because of the third law of motion, the equal and opposite force. Now if I consider this section of the string, then it is a stretched section. It will pull both the ends with the equal amount. So T and T over here. This is also a stretched section of the string. We have in fact discussed that the tension is in a string is same all over, provided there was no friction. In this case, there was a lot of friction, so the tension this side was not equal to the tension on that side, which I could feel in my hand. But if there is no friction, then the tension will be same all over. So if there is friction, how the tension varies, that also we are going to discuss later. So even if there was friction and there was some other tension this side, it is a light string, then say T dash and T dash. even if there was friction. Then I managed with a F pull, which was equal to T, with a T pull in fact, I managed T plus T dash pull on him by having a smarter way of doing my job. I took the help of the wall. One end was the wall. If the wall was weak, this gets ripped off, my whole plan goes for a toss. So that's your tension force. So when we do problems, you'll understand it much better if you have not already understood it. So 3 points again. In a string, tension, in a stretch section of a string, tension pulls both the ends. The tension on both the ends would be of equal amount if the string is massless, and if it is one string, then the tension is same all over as it goes around the pulley or whatever. If the string is massless and the pulley is frictionless, then it will be same all over. So that's your tension force. So next is normal reaction.